Okay. Let me end this meeting because I think you have started this meeting. Okay, so it is recording now, so that's fine. So in the last class, we discussed about the axial pumps and centrifugal pumps. So in this class, we are going to start discussing the fundamentals of turbine. So for that, let me take here my whiteboard. Okay, so I have shared a whiteboard with the class, and I am quite hopeful that you can see it on your screens. So now we are going to discuss turbines. So what is the function of turbine? It has been used for quite a while now, maybe more than a century. The basic purpose of a turbine is to convert the mechanical energy available in rivers or wind into useful mechanic, mechanic I should rather say electrical work, electrical energy, or we can also call it useful mechanical energy, right? Through a rotating shaft, right? So if you remember that in case of pump, when we were talking about pump, this rotating shaft was impeller, like in centrifugal pump, right? But in case of turbine, this rotating shaft is called runner for turbines. So this is different terminology that whenever we would talk about the rotor of a turbine, then we would say that it is a runner. But in case of pump, we call it impeller for the centrifugal pump and propeller for the axial pump, axial pump or fan. Impeller, and we can also call here it is a propeller, right? Impeller or propeller, right? So now if we talk about the types of turbine, in reference to with reference to working fluid, that what working fluid we are using for the conversion of mechanical energy into electrical energy or useful work. So first of all, if the working fluid is first of all, we talk about hydraulic turbines, hydraulic turbine or hydro turbine. We call it hydro turbine. When the working fluid is water. So one of the prime examples for that is these dams we usually construct, like Turbine Dam, Mangla Dam. So they use hydro turbines for the conversion of the mechanical energy available in water into useful mechanical work, which is subsequently converted into electricity. Okay, so one is that. What else? Maybe wind turbines. Like we use uh, the mechanical energy in the air to kind of convert into useful mechanical work, and we can see the installation of wind turbines at places where we have got high winds. So usually we can have wind turbines installed in those areas. Okay, what else? We have got steam turbines. So where do we see steam turbines in steam power plant? So in this case, the boiler is used to convert water into steam, highly pressurized, superheated steam, like you must have studied in thermodynamics too. And then we can employ that superheated steam to strike the runner of a steam turbine, and then we can extract useful mechanical energy from that. Right. Anything else we can think of? So, where do we see steam turbines? Eh, they are usually coal-based power plants. So, coal or nuclear power plants. So when we say coal or nuclear power plant, so we are saying that we are using burning coal to convert water into steam, or we are using that nuclear fission process to convert the water into steam. So that is just the source of energy we are talking about, coal or nuclear power plant, right? And then the fourth one is gas turbines. So in gas turbines, we combust uh, some fuel like diesel or petrol. Mainly, we employ diesel in this, and then we can kind of generate electricity. So these are the turbines which are or like these are the diesel generators which we usually install at our home, or petrol, working on petrol, and then all the IPPs which are usually provide electricity. Independent power plants, they usually employ gas turbines in their gas power cycle. So we are talking about gas power cycle here. So these two are three bits. We usually cover them in thermodynamics to steam power cycle, gas power cycle. So because here we are talking about fluid mechanics, so usually we talk about these hydraulic turbines, which uses water as a working fluid. Uh, so our main focus here in this course would be hydraulic turbine, right? So usually these hydro turbines, or in general the turbines, have higher efficiency in the range of maybe around 95% for the turbine, as compared to pump, which is basically it is from 85 to 90, or maybe 80 to 90%. So there are certain reasons for higher efficiency. So first of all, because in case of pump, the rotational speeds are high. speeds are higher in case of pumps. So that leads to higher frictional and shear losses. Higher frictional and shear losses. Right? And so this is one reason that why turbine has got higher efficiency as compared to pumps. Then there is another reason that for this higher efficiency, that the conversion of low energy into kinetic energy, which is the operation of kinetic energy of rotor blade in turbines, is have less losses as compared to the vice versa. Because in the pump case, what we do that we convert. So this is the kinetic energy of the blade. We usually call it kind of flow energy. Sorry, uh, flow energy. It is the kinetic energy of the rotor blade. So what is flow energy basically? Flow energy is the pressure, basically pressure and velocity. So the pressure and velocity of the flow, it is being converted into the kinetic energy of the rotor blade, right? But in pumps, what we do that is the reverse process, that we use the kinetic energy of the rotor blade to give high pressure and velocity or velocity to the flow. So that is a reverse process. So this process of conversion of flow energy into kinetic energy, that is more efficient as compared to the vice versa. Then we have got another reason for that hydro turbines are usually larger in size, larger in size as compared to pumps. So viscous losses are less important. Then we have got another reason for the higher efficiency of turbines, that is that usually pumps are designed to operate in a wide range of wide range of volume flow rate. So they are not very efficient, right? But whereas not we should not use, while turbines are designed to operate in a narrow range of volume flow rate, right? So that's why we can kind of optimize turbines very easily, because the range of volume and the range of volumetric flow rate involved in turbines that is quite narrow, so that we can design it accordingly to have the maximum efficiency. But that cannot be done for the pumps, because the pumps are required to operate in a quite wide range of volume flow rate depending upon the application. So these are the four reasons that why the turbines have got a little bit higher isentropic efficiency, let's call it, as you discussed in thermodynamics course. So it has got a little bit higher efficiency as compared to pumps. So we usually use turbines for power production, but they are also used for volumetric flow rate measurement. If I can show you the example of that, maybe just a minute, can show you the example that where it can be used for the volumetric flow rate measurement. So just a minute. So just example that. So in this figure, you can see these half cup type anemometer, right? So they are used by meteorologists to measure the wind speed. So when we can measure the wind speed, then we can also measure, because if the wind is moving with the higher speed, the rotation of these uh, these the shaft which is attached to these three semi cups, that would be kind of mode, and then we can measure the speed of the flow. So meteorologists usually use this kind of arrangement, but normally speaking, or generally speaking, turbines are used for power production. Like I have explained the four different types. Well, like if you can see here that we have got hydro turbine, wind turbine, steam turbine, and gas turbine. So they are widely used in industry. So now we have got another type of turbines with respect to net head and volume flow rate. So there are two types of turbine. One is impulse turbines, and impulse turbine, and the second type is reaction. So in impulse turbine, the net head required is higher head requirement, but it can operate for situations where the volumetric flow rate through the system is lower. So lower volume flow rate required. On the other side, for the reaction turbine, the head requirement is a little bit lower head requirement, but it usually requires higher volumetric flow rate. So what are the examples which we usually see for the impulse turbine? So usually we say that there is no pressure decrease in runner. In runner, or we can say rotor, right? No pressure decrease.
सर impulse turbine और Synd turbine में सन क्या फर्क क्या होता है?
बेटा ये impulse turbine जो सा है जी उमर इधर तो उमर खालिद
Yes sir.
जी उमर ये जैसे कहा गया कि ये जो impulse turbine होता है it can operate for the low volume low volumetric flow rates, but it requires higher head. Higher head means that higher difference in pressure, right? But for the reaction turbine, it can operate for lower pressure difference, but the due to the lower pressure difference, the volumetric flow rate should be high, right? Now I am talking about in terms of pressure decrease in a stage. So in case of impulse turbine, the pressure there is no pressure reduction in runner, but in case of reaction turbine, pressure decrease occur partly in stator and partly in rotor. In case of impulse turbine, all the pressure decrease occur in stator or nozzle. We call it nozzle. Is it clear, Matt?
Yes sir.
So you need. So maybe you must have kind of come across these two types in your thermodynamics course as well. Is it true? Have you heard these names, impulse turbine and reaction turbine, during your thermodynamics 2 course? Is it?
सर impulse turbine पढ़ा है.
अच्छा
सर
तो
impulse turbine
उसमें
reaction
यही
turbine किया.
अच्छा लेकिन वो भी इंशाल्लाह आप देखेंगे हो सकता है कर लें ड्यूरिंग टाइम लेफ्ट इन दिस कोर्स. तो उसके अंदर आपने यही पढ़ा होगा ना कि सारा जो प्रेशर ड्रॉप होता है दैट अकर इन द नोजल इन केस ऑफ impulse turbine and there is no pressure decrease in the rotor part, while for the reaction turbine the pressure drop occurs partly in the stator and partly in rotor. So what are the examples? Now we are talking about in terms of hydro turbine. So for the hydro turbine, the biggest example of impulse turbine is Pelton wheel, right? And the examples of reaction turbines are Francis turbines and Kaplan turbines. Right, so Francis turbine is usually used in dams like the Villa Dam, Mangla Dam. So these kinds of dams usually use reaction turbine for the operation. So Pelton wheel is let me show. Now we start discussing about the Pelton wheel. So let me show you the schematic of a Pelton wheel, and then we can have a discussion on that. So for the Pelton wheel, let me copy the figure and then Okay. So it is kind of a it is kind this this is the you can say that it is the kind of front view for Pelton wheel. You can see these uh, these blades which are installed on the periphery of a large disc, right? So the ability radius is the for that is r, and then the shaft on which this disc is attached, that is into the board, right? And it is rotating with velocity omega, right? And then we have got our nozzle installed here. So you can see that what is the use of nozzle, that it converts the pressure or flow energy into kinetic energy of the jet, and then that jet is being imparted on the these blades, and then when it strikes the blade, so what happens, that if we see this blade from the maybe from the bottom side, we can see a splitter kind of arrangement here. So what does it do? That whatever water is coming here, half of the water would go in the reverse direction in this way, and half of the water would go in this way. So we usually have this splitter plate. Otherwise, all the fluid would be entrapped into this, and maybe it would go downward rather than go sideways, because uh, this change in direction of velocity would impart the net force on this blade, and due to this change in direction for the velocity jet, there would be a net force in the from left to right. So that's why this whole disk would move anti-clockwise, right? So basically, it was proposed by a scientist named Lester Pelton, maybe at the end of the 20th century, so maybe 19th century. So it has been in operation for the last maybe more than a century now. So so now we can, so basically if we want to get the maximum energy out of the flowing water, so ideally you can see here that this change in direction of that jet should be kind of 180 degrees, and it would have been maximum energy extracted from the jet. But practically speaking, we cannot do that, because from here, if it is striking the blade and then reversing it, then it is going to eventually strike with the incoming jet. So that is what we don't want. So basically, this angle is normally between maybe 160 degree or maybe 150 to 165 degree. This angle beta. It is not. It cannot be 180 degree. Otherwise, there wouldn't be any striking of jet with the blade, because all the jet which has been coming back from this blade, it would strike with the incoming jet, and there wouldn't be any any striking of jet on the runner blade. So let me show you a small video for this for the operation of this content wheel, and then we can take it from there. Just a minute. Can you confirm that you can see the video which I have shared? At the moment, it is not being played, but can you see the screen, the map?
Yes, sir. Yeah, sir.
Okay, you can see it, so that's good. So let me play it, and then afterwards we will discuss it maybe in the subsequent lecture. Okay, one thing that there is a this is the nozzle which is attached here. So this nozzle is going to send water on this these blades. And one thing you can see here that there is a cut, there is a gap here. So it is just to make sure that the water strike at the blade which is exactly at the bottom of the turbine, so that it doesn't strike here, rather than it strikes when the runner blade is at the exactly at the bottom of this, so that it can impart the maximum tangential force which is required for the torque. This is a spearhead, so if it would go uh, inside the nozzle, the volume flow rate would decrease. But if it comes out, so it means that the maximum volume flow rate can move through this nozzle. Okay, so these 2 points are similar to the shut-off hat and free duty point, as we discussed in the case of pump. So first, if the this is a case that when we have got the flow is coming on this, but that wheel is stuck. So it means that impulsive force would be maximum in first case, that if the wheel is stuck, but because it is not rotating, so power generation is zero. And then the second thing is when it is rotating at the same this tangential velocity, which is u is equal to r omega, that is the same as the jet velocity. Then even then, because the flow is not going to strike the blade and it is not going to impart any kinetic energy. So in that case as well, there is no useful power which is going to be gained by this. So usually the if we plot the efficiency, then the maximum efficiency we usually get when we have got the it is half, when this ratio is half V bucket of we get when it is half. Right? So it means that if the bucket is moving with a velocity of maybe rather I would say that if it is moving with a tangential velocity of 10 meter per second, then if we want to get the maximum power out of this Pelton wheel, then the jet velocity should be 20 meter per second, right? So in order to have the best power performance of the Pelton wheel. Okay, so this was it from the slide. So you must have picked a few things. So let's see the equation for the Pelton turbine. Let me share the lecture slides now. Okay, so hopefully you can see the lecture slides here. So as I told in the introduction for the impulse turbine, that we use a nozzle for the impulse turbine, and all the pressure is converted into kinetic energy of the jet in the nozzle, and there is no pressure change when the that fluid hits the bucket or blade of that impulse turbine, and then there is an impulsive force. So impulsive force means that it is being generated due to changing direction of the jet. So as we discussed that ideally it should be 180 degree, but it cannot be 180 degree due to the fact that if it is 180, then it is going to strike with with the incoming jet, and then there wouldn't be any very efficient mechanism for power extraction. So that's why beta value, which is the angle shown here, that is usually in the range of 150 to 165 degrees, right? So now, if we want to see that then that as discussed in the video, there is a cut here at the end of the bucket, so that the water can strike the bucket n rather than bucket n plus 1, because we don't want it to strike here. We want it to strike somewhere at the bottom blade, which is bucket n. So that's why there is a cut at the top, at the this side of the at this side of the bucket. And then, as shown in the video as well, that there is a separation or splitter arrangement here, just to divide the jet into two portions so that it can go in opposite direction. So, right. So this is a close-up view of a Pelton wheel, which is installed in a practical situation. You can see that splitter is here very clearly. Then you can also see here that cut we are talking about, right? So these are the practical installation of Pelton wheels. So then a view from the bottom of an operating Pelton wheel, it is showing that splitting and turning of the water jet in the bucket. So this is kind of the cut here. We can see very clearly, and we can see that due to this cut, this water jet is going to be hitting this bucket rather than most of the jet would be going to hit this bucket, which is right at the bottom. Right? It is not going to hit this bucket, which is shown here. Right. So now the center of the bucket moves and tangential velocity r omega. So what is r here? That is the mean radius, right? Because at the base there would be a base of the bucket, the radius would be a little bit less as compared to tip. But because we are assuming that this on which the bucket is installed, that has got a very large diameter as compared to the this height of bucket. So that's why we are using we are taking a mean radius. We are not taking R1 and R2. We are just assuming that the radius of this wheel, it is quite large as compared to the height of this bucket. Right? Any question? So now the solution is simplified by assuming that the entire jet strikes with the bucket at the bottom of the wheel, bucket end, and the effective radius of the wheel is R. Is R, which is quite large. So we are just ignoring the height of the that bucket. So in addition, it is approximated that the water is turned through angle beta without losing any speed. So it means that whatever the jet velocity was here, the same velocity was here. But because now we have got the frame of reference a little bit different, so the velocity which is coming here, that is Vj minus r omega, right? That is the velocity which is being experienced by an observer which is sitting on this plate, Vj minus r omega, right? That is the relative speed, as we discussed in the case of velocity train. So, if we want to write the power output of our Pelton wheel, that is the basically the rate of change of momentum. So, basically, it is the angular momentum at the inlet minus angular momentum at the outlet. So, now you need to understand one thing here, which is I found it a little bit confusing in the book. So that is here V2T is the inlet velocity and V1T is the outlet velocity from the bucket. So basically, for the because inlet velocity, inlet energy or momentum of the fluid would be larger than the outlet angular momentum. So that's why there would be a useful work which is going to be collected on the generator. So, but in the case of pump, the angular momentum out of the fluid is greater than the angular momentum of the inlet of the fluid. So that is totally opposite. So for turbine, it is conventional to define point 2 as the inlet and point 1 as the outlet. Because it was a little bit confusing, so I just kind of thought that it is good to write it here. So now, if we want to see that what is V2T in this case. So V2T is if we see it from an absolute reference, yes, anything, any question? Because someone unmuted the mic, so if you have got any question, you can ask. Okay, maybe it was just by mistake. So in this case, what would be the V2T with respect to an observer which is on a ground level, on a stationary frame of reference? For that, V2T would be equal to Vj, right? That would be just a jet velocity. But what would be the V1T? That can be determined by the velocity triangle. That would be R mega is the tangential velocity of the blade. Then we have got V1, that is the absolute velocity, but we need to calculate V1T. So if we use this arrangement, R mega is in this direction, Vj minus R mega is in this direction. So if we calculate V1T, that would be equal to R mega. It should have been cos of 180 minus beta, that is minus cos of beta. So here it should have been minus because of the change in direction, but because we're using this identity, we can write V1T is equal to R mega plus Vj minus R mega, Vj minus R mega into cos of, actually equal 180 minus beta, but we can write it Vj minus R mega cos of beta, right? So the only thing left now here is just to put these values. So here we can put the value Vj, and then instead of V1T, here we can put the value R mega plus Vj minus R mega cos of beta. So if we put these values here, then we can see Vj. Here one thing we have done, that R2 is equal to R1, which is equal to R. So we have taken R common. So V2T is equal to Vj, and instead of V1T, we are putting this expression by using this velocity triangle. So if we put that, we come up with this. So Vj minus R mega, if we combine it here and as well here, so we can also take Vj minus R mega common out. Then it would be 1 minus 1 minus cos of beta. So Vj minus R mega, that has been taken. If we put bracket here like this, then we can take this common, then this would be also common out, and then 1 minus cos of beta. Now the maximum, by this relation, if we want to see that what is the maximum power which can be extracted, that can be when beta is equal to 180 degrees, because in that case cos of 180 would be minus 1. So 1 minus into minus 1 plus 1, so it would become 2. But from the practical constraint, we can see that beta cannot be 180 degree, as I have explained many times, that if beta is 180 degree, the fluid which is going out, that is going to eventually strike with the incoming jet, which is not desirable. So that's why we don't want that. So in practical situation, it is around 150 to 165. They have written 160 to 165, but practically it is in the range of 150 to maybe 165. So if we want to calculate the efficiency factor, that is the actual power which is getting out of the blade, and the maximum which can be extracted when beta is equal to 180. So that is the formula for the efficiency. So if the beta is 160 degree, then efficiency of Pelton turbine would be 0.97. So it means that only a loss of about 3%. So as we mentioned in the beginning, that we usually have more efficiency for the hydraulic turbine. So And then the last bit is that we can calculate the the velocity of the jet at which it would have the maximum efficiency. That would be when we have got the jet velocity, which is 2 times the tangential velocity of the bucket, right? So the jet velocity would, and it was also mentioned in the video as well, that if the jet velocity it is uh, twice the tangential velocity of the bucket, then we would have the maximum efficiency in this case, right? So those are the cases. If Vj is equal to R omega, then we wouldn't have any output work. So V not turning, or if R omega is equal to 0, then also V is not going to turn. So in both, these are both limiting cases, as it was also for the pump. If you remember, for the pump we had shut-off head, and then shut-off point, and then free delivery point. So shut-off point, if we say that it corresponds to R omega is equal to 0, when wheel is not turning or pump impeller is not turning. And then if R omega is equal to Vj, then it means that it is the delivery point, that the incoming jet is not going to impart any momentum on the angular momentum on the bucket. So that's why there is no use of that as well. And if we say that the jet velocity is equal to tangential velocity of the bucket, so that is of no use. Usually Vj should be greater than that. It cannot be less than the R omega value. Otherwise, we are going that jet would be going to extract the energy out of the turbine instead of providing it. Right? So that is something which we want to make sure that is not the case. So I hope that today's lecture was a little bit of help in understanding the concepts of uh, pattern wheel or pattern turbine. So I would take the attendance now. So if there is any query, you can ask now. And then secondly, there are a couple of announcements that I want to make. First of all, the first announcement is that you are going to have your second quiz in 2 hours class on this coming Tuesday. So it would again be an MCQ based, and you would be given maybe 10 MCQs and maybe 50 minutes, or I would see. And then it would be up till only pumps. You don't need to cover this Penton wheel for this. So only up till pumps. From the start of the turbo machinery or that velocity triangles and things, and the basic concept we discussed before the start of turbo machinery, which is chapter 6 of that single group. So this is first announcement, and second announcement, maybe Hashir, are you there?
Yes, sir.
Okay. Hashir, can you please spread the word that any student who hasn't submitted any of the assignment or the project, he can submit it right now, and I would consider it with late submission. So, and he would get significant or considerable numbers. So it is always better to have like uh, some numbers instead of 0 mark. Okay? Otherwise, because you know that here the progressive assignments, they carry quite a lot of weightage. So uh, please ask that I have checked your first 3 assignments. So there are many students who haven't submitted many of the assignments, maybe a couple of assignments. So please ask them to submit the assignment, and so that I can check them and uh, please submit it. Otherwise, if it is 0 marks, maybe uh, one assignment carry like 4 absolute marks, and the project which I have given you, it carries like 8 absolute marks, right? So you don't want to miss on those marks. So please ask the students to submit those assignments by the end of